Have you ever stopped to think about how the chips inside your phone or your computer, these incredibly complex little things, actually manage to work without constantly crashing? Well, I can tell you it's not magic. It's this brutal, really clever process called verification. So yeah, let's dive into this hidden world where the whole job is to try and break things before they ever get to you. To really get why this is so critical, you have to start with this number, 10. This is what's known as the 10x cost rule. And what it means is finding a bug while the chip is still just a design on a computer, that's relatively cheap to fix. But finding that exact same bug after the chip has been built, that's going to cost you 10 times more. And finding it when it's already in a customer's hands, well, that's a full-blown catastrophe. So yeah, the stakes are unbelievably high. So, to even survive in this high-stakes game, verification engineers have to adopt this totally backwards-sounding philosophy. Bugs are good. It's kind of wild, right? Their entire job is to be the bad guy, to torture the design, to think of the most devious things they can do to it, all to find every single hidden flaw. Because every bug they find now is a win. It's one less 10x disaster waiting to happen down the road. Okay, so what is a bug, really? In this world, it's actually super simple. A bug is just any time the hardware does something different from what the official plan, the specification, says it should do. That's it. If the spec says when you add 2 and 2, the answer is 4, but the chip spits out a 5, congratulations, you found a bug. The entire job is to make sure the reality of the chip perfectly matches the contract laid out in the plan. So how did engineers first try to hunt down these bugs? Well, they started with a pretty logical method that, as we're about to see, had some really serious blind spots. They called it directed testing. And you can just think of it like a giant checklist. You literally list out every single feature the chip is supposed to have, and then you write one specific test for each item. Test 1, does adding work? Check. Test 2, does subtracting work? Check. It seems logical, right? But it has two huge problems. First, it is a ton of manual work. And second, and this is the real killer, it only finds the bugs you were already expecting to find. It can't find the weird stuff you never thought of. You know, the flaws in that old checklist method were so big that it forced a total revolution in testing. And that brings us to the new way of doing things, often called constrained random verification. And this really shows you the difference in a nutshell. The old way was all about manual effort that just couldn't scale. The new way, this constrained random approach, is about building one single, smart, reusable system that basically writes its own tests. Now, yeah, it definitely takes more time to set up at the beginning, but the payoff is massive. It's designed to sniff out those unexpected, tricky bugs, the ones you never would have put on a checklist. And it can actually keep up with the insane complexity of modern chips. So how does this whole modern testing thing actually work? What's the magic sauce? Well, it's really powered by two fundamental big ideas that we're going to break down right now. The first big idea is the absolute engine of modern verification, smart randomization. And the key word here is smart. This isn't just throwing random garbage at the chip to see what happens. No. Instead, you give the test system a set of rules. We call them constraints, like create a valid network packet. And then you just let the computer go nuts, generating thousands upon thousands of different but still valid packets, exploring way more possibilities than a human ever could. So what kind of stuff do you make random? Well, there are 4 really crucial areas. You randomize the main data coming in. You randomize the timing and delays between different signals. And you even randomly inject errors on purpose to make sure the chip can recover. But the most important one, and this is the #1 place bugs are missed, is the chip's settings. Randomizing every possible configuration is just absolutely critical to finding the deepest bugs. But this brings up a huge, obvious question. If you're just running thousands of random tests that the computer is making up, how on earth do you know when you're finished? How can you possibly be sure that you've actually tested everything important? And that leads us straight to the second big idea, functional coverage. This is the answer. If smart randomization is the engine, then functional coverage is your GPS, your steering wheel, and your progress bar, all rolled into one. It's a totally separate piece of code you write whose only job is to watch the random tests and measure which specific features and scenarios have actually been hit. And these two ideas, they work together in this beautiful feedback loop. Here's how it goes. First, you run a whole bunch of random tests. Second, you look at your coverage report to see the holes, all the stuff you missed. Third, you add new rules to steer the randomness toward those holes. And fourth, you just repeat that whole cycle over and over again until your coverage report finally hits 100%. Okay, so we've got the core ideas down. Now let's just take a quick peek at the anatomy of one of these tests to see how all the pieces actually fit together. Modern tests are built in layers, kind of like a cake, where every layer has a very specific job. Way at the top, you've got the conductor, which basically just says go. Below that is the story layer, which defines a high-level goal, like send a video file. The real heavy lifting happens in the brain, which breaks that story into smaller tasks and checks all the results. And then at the very bottom, you have the hands, which are the bits that actually wiggle the digital wires and talk to the chip. It's also really important to know that all this testing happens at different zoom levels. You start small by testing just one tiny piece, a block, which is really fast and simple. Then you integrate a few of those blocks together to see if they can play nicely. And finally, you test the whole system, the entire chip at once. Each level gets slower and way more complex, but they all find different kinds of bugs. And all of this incredibly detailed work, all these layers and feedback loops, it all leads to a final profound lesson, something known as the verifier's paradox. And the paradox is this: you can never, ever prove that a design has zero bugs. It's impossible. No amount of testing can prove a negative. There is always the tiny chance that some bizarre 1 in a trillion combination of events exists that you didn't test for and that will cause a failure. So, if you can't prove perfection, then what can you prove? What's the whole point? Well, you can prove that you have tested 100% of your plan. By hitting 100% on your functional coverage report, you are proving to the world that every single feature written down in that specification has been completely and thoroughly exercised. You aren't proving the absence of all bugs. You're proving the completeness of your verification. And in the high-stakes world of making chips, that's everything.